Hello everyone, this is Dr. Lennon, and today we're going to continue with 3.2. So this is polynomial functions and their graphs. We've already looked at linear functions, quadratic functions, so these are special cases of polynomial functions. So in general, they're going to have some things in common and some things that are different. We've also looked at y equals x cubed in our basic library of functions. But basically, we're going to be focusing on two main things, their end behavior, so what happens as you go all the way out towards a positive and negative infinity, all the way to the right and all the way to the left, whether the graph rises or falls. And we're also going to be looking at what happens at intermediate stages. So for turning points and also x-intercepts. Okay, so the objectives, again, polynomial functions, graphing them using zeros and finding the shapes near these zeros. So maxima and minima are like turning points or hills and valleys. We'll get through all of these things, maybe not today, but hopefully through Friday we will. So let's go ahead and get started. So a general polynomial function, what is it? Well, it's just a collection of a bunch of terms where you're allowed to multiply by regular numbers and raise x to whole number powers that are positive. So there are some special terms. I mean, it may look a little confusing, the definition right here. P of x equals a sub n, x raised to the n plus a sub n minus 1, x raised to the n minus 1, dot, dot, dot. There's some special terms. So the two of note are the leading term, so a sub n x to the n, so that's the leading term. The leading coefficient is that a subscripted by n. The degree of the polynomial is n, so that's the biggest power of x you'll see anywhere. And then our constant term is a sub 0. So basically all of our n behavior is going to be determined by that leading term. So we're going to be focusing on two things when we look at n behavior, whether a sub n is positive or negative, and also whether n is even or odd, because remember n has to be a whole number. So let's go ahead and move on from there. Again, the definition looks really complicated, but as we work with it, you'll kind of get comfortable with what a polynomial is, and maybe you already are. Okay, so there we go. Here's an example. Basically, notice all the powers of x are whole numbers and positive. The leading coefficient is 3x to the fifth. The constant term is negative 5. The leading coefficient would be 3. The degree would be 5. So then they list all the coefficients, but really the two important things to focus on are identifying the leading term and the constant term, and then the leading coefficient and the degree of the polynomial. So this is just an example of a polynomial. Okay, then here's some other examples. There's some special names based on how many terms there are. So if you have two terms, it's called a binomial. If you have just one term, it's a monomial. 3 terms, trinomial. Polynomial is the most general. It could stand for any number of terms, but again, here you see the degree in the leading term and also the constant term being identified. Okay, so let's talk about the graphs, which is mostly what we're going to be focused on. So there's two cases, even and odd, as you see here. Y equals x, that is a degree 1 polynomial function. So we see in this current case, it falls to the left and rises to the right. Whereas in contrast with y equals x squared, which is a degree 2 polynomial function, which we would say has even degree, this one is rising to both sides. So these are two of our basic functions. And then we see the case happening where we have 3 and 4 and 5. So the shape is being altered a little bit, but if you look at the end behavior, that means where it's going eventually, we're kind of seeing some patterns emerge. So for x squared and x to the fourth, both sides went up, and for x cubed, and x to the fifth, the left side fell and the right side would rise. So we can see actually probably pretty quickly if you would throw a negative in front of any of those, what it's going to do is it's going to cause a reflection about the x-axis, which is actually going to invert the behavior. So for the odd functions, that would correspond to rising to the left and falling to the right, and for the even ones, falling to both sides. Okay, so basically the leading term matters more because as n becomes bigger, it becomes bigger or more dominant faster than any of the other terms. So the n behavior is kind of monopolized by that leading term, whereas the smaller terms aren't quite as important in terms of the limiting value. Okay, so here's some graphs. Again, we can recognize these pretty quickly from ones we've done. Like y equals minus x cubed, we could recognize as a reflection about the x-axis of x cubed. So it'll look just like the shape of x cubed, but it'll be reflected. So it'll be rising to the left and falling to the right. How about b, q of x? We have x minus 2 raised to the fourth. So that's going to be the same as the x to the fourth graph, but shifted 2 units to the right. And then the minus 2x to the fifth, well, we're going to have a reflection of x to the fifth. It's going to be stretched out a bit and then translated up 4. So the first one, as we can see, that the dotted or dashed line represents the original x cubed graph, and then the solid red line represents the reflection. So that's p of x, graph 1. 2, q of x, as we've seen, that's just the dotted line, the dashed graph, or dashed curve, is the original function, and then it's moved 2 units to the right. So that is the final place for q of x. And as we said with x to the fifth, it's basically kind of stretched out a bit, and then it should be reflected and moved up 4 units. Thing I don't see on this one is the reflection, so I wonder if this is a typo or what. So let's check. So the way I'm going to check is I'm going to say, okay, well, if I look at the original graph, say y. Okay. So they've already done the reflection is what's going on. If the blue graph is not the original graph of x to the fifth, that's already the graph of it being reflected about the x-axis. So the blue graph is the reflection of x to the fifth, then they stretched it a bit and moved it up 4. So that's they're just showing the final transformation in that example. Okay, so the end behavior, this is what we're talking about, where the leading term determines what's going on. All right, so one nice property about graphs of polynomial functions, they're always continuous. So the easiest way to describe a continuous function to somebody is it means that you can draw the picture without picking up your pencil off the paper. A graph like you see pictured on the slide, you have a break and a hole. So there's 2 places where you'd have to pick your pencil up and then reconnect it to the graph. So those are 2 discontinuities. However, the polynomial functions are continuous. They have no such thing on their graph. So they are also smooth. So if you get to calculus, this is the notion of differentiability. Polynomials are differentiable. I had an analysis professor in college and graduate school that told me polynomial functions are the nicest functions in the world because they don't have any sharp corners or cusps, as you see in the slide to the left. They're smooth and continuous, like the middle graph and the graph all the way to the right. So in terms of, we haven't gotten quite to the end behavior based on the leading term, but if you see both sides going up or both sides going down, you know that the degree must be even. And if you see one side going down and the other side going up, it has to be odd. So I know from looking at the middle picture, that's going to be an even degree polynomial, and the one all the way to the right is going to be an odd degree polynomial. Okay, so the end behavior, basically this is what happens as x becomes large to the right or to the left. Don't need to worry about too much besides there. Again, one thing, they talk about domain in here. If you're talking about the domain of a polynomial, it's very easy. The domain of any polynomial is all real numbers. Doesn't ever change. So it's going to go all the way to the left, all the way to the right. You can plug in any x value you want. All right, so don't worry too much about this notation. We're just going to focus mostly on the graph. Okay, so as we see, there's 4 possibilities. So the one all the way to the left, we have a leading coefficient, and because we have the left falling and the right rising, that means the degree is odd. The second graph, the degree is still odd because you have one going up and one going down, but now notice it's happening on opposite sides. Left rises, right falls. And then we have the ones where we have even degrees. So we have either both sides going up or both sides going down. They both go up if your leading coefficient is positive, and they both go down if your leading coefficient is negative. So immediately, you know, eventually all polynomial graphs have to have the end behavior of one of these 4 graphs, and they kind of have the dashed lines in between to show that the intermediate behavior could change from polynomial to polynomial, but eventually you're going to have that limiting behavior towards one of the 2 left and right directions. So there's 4 possibilities, even, odd, and positive, negative, and that corresponds to these 4 possibilities here. All right, so we're trying to determine the end behavior of this polynomial. It's very easy. We can ignore the 5x cubed plus 4x minus 7. We just focus on the minus 2x to the fourth, that leading coefficient. The negative 2, so it's negative, and then 4 is the power. 4 is an even number, so negative and even. If we go back to the previous slide, that would look like the third graph. Both sides, or excuse me, the fourth graph. Both sides have to go down because you have negative and even degree. All right, so there we go. As we see, both sides go down. All right, zeros to graphing polynomials. So zeros, what they mean by that, those are the x-intercepts. A lot of times you'll have to do them numerically. Sometimes you will see something presented in fully factored form, and when that's the case, you can determine what actually happens at those zeros based on the power of the factor. Okay. So basically, they're just saying a zero is a solution to the polynomial equals 0. So that's the same thing as saying it's an x-intercept. Again, how we're going to be able to solve that depends on what type of polynomial it is. Typically, quadratics, we can always find them because we have the quadratic formula. But once they get bigger, we're kind of left to factoring or maybe using a graphing utility. In this example, x squared plus x minus 6, it's a quadratic that we can factor, so we see it has two zeros, x equals 2 and x equals negative 3. We've already done this before. We're experts at factoring and experts with the quadratic formula, so this is kind of like a really easy example for us. Okay, so now we're going to talk about the intermediate value theorem. Basically, that says, since polynomials are continuous, if you have a y value that's positive and a y value that's negative, that means somewhere in between there has to be a y value that's 0. Imagine you're on like planet Earth and there was a railroad track that went all the way across the equator. And let's say at one point you're on the northern hemisphere and you walk to the southern hemisphere. That means at some point you had to cross the equator. That's all that the intermediate value theorem is saying. And the reason that you can say that is because we know that polynomials are continuous, which means that if you draw the graph of a polynomial, you're not allowed to pick up your pen and then put it back down somewhere else. So usually what happens is the x-axis there. So if you look at this picture, we have at A, the y value P of A is negative, and at B, the y value P of B is positive, so that means there has to be some C such that P of C is equal to 0. So this is what's called an existence theorem. It doesn't actually find the value for you. It just says, okay, we know that there's at least one place where this polynomial has to be 0. We don't know where it is necessarily. That's going to depend on, what kind of polynomial you have, if you can factor it. Maybe you have to use numerical techniques. But yeah, so we'll stop here and we'll look at some examples for graphing the intermediate behavior, what's happening at the zeros based on the multiplicity on Friday. Continue to work on your homework. If you have any questions, I'll be available by email, and I'll hopefully get back to those on Thursday. I have time to answer emails on Thursday. So again, keep in mind that homework number 2 is due on Friday before spring break. It's just 6 questions on stuff we've all gone over, nothing on this graphing polynomials business that we've done today. There is an example of graphing a couple of quadratics, which we had on test 1. So I believe if you go to test 1, number 9, the solution's there, then you'll find an example. So I will see everyone on Friday, and I will also post this slideshow under the course documents tab on Blackboard. So this is Dr. Lennon signing off.